Are we on?
Hello, I would like to, uh, hello, Georgia First community. Thank you for attending our annual symposium. Please welcome Eric, Wailing, Larry, and Alex from
Good
Team
morning, everybody.
Firestorm.
Okay, let me share the screen. So today it's really a session about 3D printing for more experienced people that are not completely new, but have been having trouble with 3D printing. So all right, so yeah, today's topic is about how to make 3D printing work better for your team. So I'm Alexander Kwa, founder of the Cherokee Makerspace and home of two FTC teams, 23638 Firestorm, and then 26, what's the other one? 481, which is going to be Frostbite. Next door to the Makerspace, I actually run a 3D print farm. So today I will walk you through three additive manufacturing technologies our team has access to, and eventually we'll see how we can make it work for your team. All right, so we have three, so it didn't switch, hold on. Okay, so for today's goals, so we have three different types of 3D printing, which is FFF is actually fusion filament printing, which is the ones you are familiar with. SLA is more like resin, and then SLS is powder. So I'm not gonna spend too much time on this slide because I want them to do the introduction. And if we have time, towards the end, we will be introducing parametric Onshape and a lightweight Onshape library that we have started developing for FTC. So, as you can see,
So I'm Eric. This is a slide about the different types of 3D printing. The first big one is FFF, which is your more common printers like Bamboo, like the Bamboo A1. This works by taking filament and then heating it up and then extruding that, laying it down line by line. In the video, it shows how it's laying down each layer of filament. This is really good. It's really good for prototyping. It's also the most affordable form of 3D printing. And there's also a wide color range because it is the most common type of 3D printing. The next big one is resin printing, also known as SLA. This produces really smooth surfaces, and this is really good because it produces really smooth and detailed surfaces. It's really good for making like detailed parts. It works by using a laser to melt and solidify resin that's in a pool, and it's perfect for small, high detail parts such as sensor mounts or intake guides that require precision. The next big form of 3D printing is SLS printing, which works by using a powder. This uses a laser that fuses the powder together. Some of the more common, or the powder that we're going to use is nylon, and which is so basically how it works is it uses the powder itself as the support structure while it's printing. So it'll melt a layer down, and then another layer of powder will go over, and then it'll just keep melting. So the unused powder is used as a support structure. This is really good for like load-bearing robot components like pulleys, gears, or custom drivetrain parts.
So just to add to Eric's discussion, powder SLS is actually the closest to our game. So you can think of yourself as the archaeologist trying to dig up the fossils from the ground because it looks exactly like it. All right.
This is just a comparison chart showing between FFF, SLA, and SLS printers. As you can see, the cost from FFF is the lowest, ranging from $300 to $4,000, where it increases in price for SLA being $1,000 to $500 for to $5,000, and then SLS is the most expensive, being tens of thousands of dollars. The next line down shows the next two lines down show the resolution. So with FFF printers, you typically have an XY resolution of 0.4 millimeters and a Z resolution of about 0.2. SLA, it has the highest resolution of all these printer types, as it has a 0.05 millimeter XY resolution and then a 0.025 millimeter Z resolution, meaning that you get really smooth and really detailed parts. And SLS comes in second, but still really good and really fine details with a 0.2 millimeter XY resolution and a Z resolution of 0.11 millimeters. Surface. Oh.
Next one.
Yeah.
Oh, what happened? There we go.
So
So now we're going to talk about go into detail on filament, and I have Waylon here to talk about it more.
So equipment overview, we have 4 different basic types of printers. You can have a bed slinger, which is the cheapest type. It's a bed slinger. Usually they are, it's the photo right here.
Oh, yeah. Yeah.
Photo right there. It's,
Oops, sorry. There you go. That's the bed slinger. It's the smallest one in the group.
it slings its bed around, giving its name, where only the bed moves and the head is stable on one axis. For the core XY, this moves where the entire head can move all around, and then the bed only lifts up and down. This is the best. This is the cheapest, second cheapest for good, decent quality 3D printing. The bed is easier to move as it doesn't require the same as bed slingers. It's faster. Bed slingers will slow down with extra weight of the prints on it, but with Core XY, the head is the only one that moves. Now moving on to Core XY multis. These are printers such as the Prusa XL, where the heads are able to be swapped out for quick, fast, multi-material or multicolor printing. Last one is the Core XY, the largest one, the Elegoo Onshape Giga. This one's a very large Core XY printer. It has the dimensions of 800 by 800 by 1000. It's very big in person.
Yeah, so these four machines actually are available at our makerspace, so that's why we featured them here. We have experience with them, and the kids get to use them. So I guess that's you, Larry.
What's stronger, 3 perimeters with a 0.4 millimeter nozzle or 2 perimeters with a 0.6 millimeter nozzle? I guess you can use the chat to answer.
Okay, well, we'll just stop for 5 seconds and go ahead and provide the answer, because we might run out of time.
The answer is 6 millimeter, 0.6 millimeter nozzle, because it lays down wider, taller beads with fewer seams, meaning stronger, faster prints with fewer weak points. You'll lose a bit of fine detail, but it's more than good enough for most FTC robot parts.
Thank you.
Oops. So this next slide is about these next few slides are about some of the filament types that you'll see in robotics. The first one is PLA. This is the most common type of filament, where it has a very wide color range, but at the same time is very brittle with low impact resistance. And it's really good for prototyping and test fitting, but you shouldn't really use it for high impact parts because of its brittleness, it will snap and shatter, meaning that it's not that reliable if you're trying to make something like mounts or shaft colors, because it just doesn't have that longevity. The next most common type of filament is PETG. This is, I think, the most common in robotics, but it's tougher than PLA and it doesn't shatter. And it's really good for medium load parts like belts and pulleys and simple mounts and brackets. because it can take on those multiple, like it can take on multiple hits and won't shatter. Now it's not as strong, it's kind of like the middle, but this leads into the next, or one of the next filament types, which is ASA. This is what PETG is in the middle of. It's basically a blend of PLA and ASA, where ASA is extremely tough and impact resistant. It is also stiffer than PETG, and it's also less brittle than PLA. But with all these added benefits, there is you do have to print with enclosed and ventilated printers because it does produce fumes. Now, one of the more niche filaments that you can use is PACF nylon. This is one of the highest strength and impact resistance filaments that you can use on the market right now. It is really good for structural parts that require stiffness, like like for our elevator that we're going to show later in the presentation. We use PACF nylon because it allowed us to get super thin walls and use barely any filament, but also hold hundreds of pounds. You do need to print it with enclosed and ventilated printers because it does also produce some fumes. And TPU is another type of filament, but it's more similar to, like, let's say a rubber or a silicone because it is both flexible and impact absorbing. It is really good for compliance structures like wheels and wire management, and you can also use it as like intake mechanisms and claws. And
It's actually also good for bumpers.
yeah, it is also really good for bumpers because of how impact resistant and absorbing it is. A good way to combine two, if you have the access to like dual head printing, is using a PETG/TPU print, where in this picture it shows a wheel that has a PETG solid core, and then it has a TPU.
I don't know if they can see my video, but that's an example of a wheel that has a PETG center. Go ahead.
Yeah, so basically, when you use a PETG core and then a TPU wheel, it allows that wheel to have both structural like rigidity and not break as easily, but it also has the added benefit of being a wheel and actually having that compliability.
Thank you. All right, Larry.
Another trivia question. What's the number one cause of weak fused filament prints? The answer is poor layer adhesion. Strong walls and good layering bonding matter more than packing in extra infill.
Thank you, Larry.
So a big thing that affects layer adhesion is print speed. This is because, well, I guess it should just say, when I think we've all done it, where when we're trying to start a print, we put it on the printer and we're gonna bump it up to more and more speed just to try and get it off the printer even quicker. That's good for getting prototypes done quick, but there are noticeable downsides in printer quality because the layer adhesion does take a hit, because as you're printing a layer, when you're printing a layer, it has to have the filament has to have time to actually cool down and adhere to the layer below. And when you print when you raise the print speed, it gives even less time for that filament to cool, thus reducing layer adhesion and parts rigidity.
In FFF, parts are strongest along the layers and weakest between layers. So, for example, a tall vertical part will be weaker because there's more layers. The same part, if you rotate it 90 degrees to orient it horizontally, will be stronger and more durable. The pictures on the right side, the top left picture, the part is weak if you pull it in that direction because the bond in between the layers are weak. Beneath that, it's strong if you pull it in that direction because the bond in each layer or along the layers is strong. And the bending is strong because it matters along the layers and not in between the layers. Bending the part parallel to layers is weak because it can easily break because the bond between the layers is weak. And
All right,
Next.
that's it?
Yeah.
Okay.
Will you save time switching from a 0.4 millimeter nozzle to a 0.6 millimeter nozzle? A 0.6 nozzle lays down fatter and taller beads with fewer seams, which is better interlayer fusion and fewer weak spots. Print speed depends on filament type and flow characteristics. Oftentimes, printing with a 0.6 millimeter nozzle only provides a marginal improvement in speed.
Thank you, Larry. There you go.
So these are adhesion aids. Adhesion aids are needed because plastic shrinks as it cools. The bigger the surface, the greater the tendency it has to warp. PLA and PETG normally don't need any glue, but like with ASA, it needs a heated chamber, otherwise it will warp. So for our first type of adhesion, it's brim. Brim is just a slicer setting. It's just you set it down, slice, and print. Brims are useful for tall and skinny prints. They keep the part from toppling over. So if you have spacers, they tend to fall over sometimes while printing. You can add a brim on them to keep them from falling over. Next is helper discs. Filament contract as they cool. So on large prints, large flat prints, corners tend to warp more. So helper discs improve adhesion by increasing surface area at these corners. You can add this in the slicer, but it's easier to add it in CAD. So last one is slotting. Slotting breaks up large flat surfaces. Breaking up the first 3 layers into smaller sections could prevent the warping as you get smaller sections cooling instead of a large big surface cool.
Now, another big part of 3D printing is infill. Think of infill as like the skeleton of your structure, where you have the walls and perimeters that provide the rigidity on the outside, but if there's nothing to hold it in on the inside, it's just gonna fall, it's just gonna collapse. Going from 0 to 25% infill adds a whole ton of strength because you're basically going from nothing to a really well-defined skeleton structure inside your print. But anything above 25%, it adds marginal increases in structural rigidity because the walls take over from that point. As you can see by this picture, there's a whole ton of different infill types, but generally the one to go with is gyroid because it's a good all-rounder infill that's strong in all directions and fast and easy to print. For something, let's say you're using compliant filaments, you could use concentric because it allows for the compliant filament to actually squish because it doesn't have things going in between the infill. It just provides support in one direction, allowing it to squish in another. But you do also want to avoid using rectilinear,
This one.
because that leads to a lot of blobs as the infill pattern crosses over, which can reduce its actual structural rigidity. Another big part of 3D printing are seams and perimeters. Seams are basically where one layer begins and ends, and typically when you do it in a slicer, they're all lined up in one straight clean line. This does make your print look better, but it also induces a great point of failure where if that seam has a lot of force applied to it, it's more likely to break. A great way to get by this is making your seams random, where they're spread out across the entire face of the print, which allows for the potential risk of having seams be spread across the entire face of the print, improving how structural that wall is. The next big point is perimeters, as these are the most important part of your 3D print and provide the most support. A big thing when you're making your perimeters is you kind of want to match your perimeters to the size of your nozzle. So let's say you're shelling a part, you want to make sure that shell thickness matches up with the size of your nozzle. And a great example of this is using a 2.4 millimeter shell, because this matches up perfectly with both 0.4 millimeter nozzles and 0.6 millimeter nozzles, allowing for a strong and light shell that provides a lot of support.
Supports can be very useful and they can be very helpful, but they're not as good as they seem because they can leave marks and they can increase print time. The best strategy is just to design to avoid them. First of all, Overhangs that are less than 45 degrees don't need supports. There are 3 tests you can do to test if your filament or printer needs supports. First one is the bridging test. This shows you how far a span of a bridge can spread out before it needs supports and before it starts failing. The overhang test shows you which angle your printer can handle and which angles your print starts to fail. The temperature test shows you the best heat settings for different printers and different filaments. With these tests, you can find out what areas you actually need support and what areas you actually don't need support. This way, you can use manual support placement to add supports only where you actually need it.
Very good.
What?
There you go.
I think it's like
Oh,
simple
come on.
as if you're already like capping out the proudness.
I'll move.
And
I'll
I want
move
to
around.
text you.
Take that seat.
Yes. Greg came in a little late, but he'll catch up. So let me play this again. So this one is an elevator that we did for our last game. It actually survived Worlds.
What? Well, like I would.
What's that? 4 seconds.
I think it's like so fast. If you're already like capping out the proudness, it's that. And I want to text you.
All right, are you ready?
Yeah.
Okay.
The carbon fiber elevator is a fast, lightweight elevator. While designing, we came across multiple design challenges. The bearings could only take a linear load, and any leaning or tilting forces would cause them to lock up. We had to add more carbon fiber rods to one stage to make sure it wouldn't lean. When on a normal drivetrain, it almost exceeds the height limit of 18 inches. So we had to shrink other parts and components to make sure it fit with size constraints.
What?
Keep going.
Like I would. I think it's like.
Who's doing flanders? Oh, okay.
The base needed to be strong enough to hold the entire elevator through rigorous gameplay. These parts couldn't support the leaning weight of the elevator. They didn't take enough advantage of the perimeters and other ways to strengthen parts.
Next.
If you distribute the weight correctly, the screws will. If you distribute the weight correctly to the screws, the parts will be strong and stable. Using the outside perimeters to our advantage, we found this design solution. We put the screws in the corners surrounded by perimeters and distribute weight through small walls around the perimeters.
So, introduction to SLA, otherwise known as stereolithography.
Lithography.
Lithography.
Lithography. Yep. All right, next.
So here's our equipment overview.
So if you want to describe the equipment for them.
Yeah, right now we're using commercial grade Formlabs Form 3. That's the printer shown in the image before. This printer is very high quality. You can print with lots of high quality engineering materials such as silicone and more. And for consumer grade resin printers, you have the Elegoo Saturn, which is a consumer grade one, a little cheaper, a little better for most teams.
Yeah, but you don't have access to a lot of the engineering filament once you go consumer.
Yeah.
All right.
So
This.
this is black or gray resin. It's a standard general purpose resin. It has moderate strength and it's less impact resistance than ABS. A good example of us using this was we use these for our custom drivetrain. We use these to print the belt pulleys and different sprockets and gears we needed. So this is durable resin. It's an engineering resin made on the Formlabs printer. It's flexible and it's impact resistant. And as you can see in the image, it's very low friction. The gears turn very smooth. So we use these for precision gears, like maybe different things. Enclosures that you would need to survive hits. You could use them in custom slides and living hinges. This is Tough 2000. It's an engineering resin. It's very high stiffness and high strength. It's very impact resistant as well. You could use it for structural components in a robot, such as the brackets and mounts, maybe gearbox housings, spacers, adapters, and sensor mounts and end effectors. is silicone resin. It's an engineering resin. It's soft like rubber. It can stretch more than TPU, and it won't break. It's the softest, most rubber-like material. We used it for custom wheels and things of that nature.
Okay.
So here's a quick introduction to SLS, otherwise known as selective laser sintering. This is a more advanced type of 3D printing where it takes, again, the powder, which it melts with a laser and has super fine precision. So a quick equipment overview that we have is we have two SLS printers, one being the Fusion 1 and then the other being the Fusion 1 Plus. I think the one I'm taking the
Yeah.
I think I'm working on the Fusion 1 Plus right now. But on top of that, we also have a sifter that's also from Formlabs, and then we have our own sandblaster to clean parts too.
So that's the actual printing, what you see on the screen. So
Yeah.
you draw the part and the laser melts the powder as it goes. So here we are actually printing test pieces. These are hole gauges for tolerance testing, bearing holes and hex, rex shaft and 4mm screws. There we go.
One of the powder types that we're going to be using this year is the nylon 12 tough SLS powder. This is an engineering SLS powder that is both very high toughness and is ductile. It has great impact resistance and it has moderate stiffness. This is the Formlabs like sample piece that shows off the nylon 12 tough powder. It's a ratcheting mechanism. It shows how even with a very small amount of with very thin tolerances, how you can have a really strong ratcheting mechanism because you can see in the center that's not really thick and it took a lot of force and effort to try and break it. Nylon 12 has great applications in motor and camera mounts, as well as servo brackets. In some cases, it can even replace aluminum or Delrin when weight matters. And we can use it as side shields for bumpers that won't crack, but they will flex instead. It's also used for clamping fixtures like shaft collars, and it can also be used for end effectors that can take repeated impacts.
Yeah. Nylon 12 SLS is, I think, 1/3 the weight of aluminum.
Yeah, it's very, very low density, but very high strength. This is another type of SLS powder. It's a TPU 90 powder. It's another engineering SLS powder, but it's flexible and rubber-like. It's similar. The 90A is similar to like shoe soles, where it can bend, but it's not going to tear really easily. It's really elastic, and it's good at absorbing impacts, and it's also abrasion resistant. This is the Formlabs. This is another Formlabs sample that shows off the TPU 90 the powder. It is a watch band that they made, and you can see how it's very flexible and durable, and it can rival custom molded rubber parts too. We can use this for intake rollers and wheels, custom bumpers and pads, as well as light duty flexible shaft couplers, and also claw grippers when used with nylon 12 for the core.
Are you ready?
I started this project to train myself for the upcoming season. As I went throughout the summer, there were many failed parts, and I found that restarting and using parts that took advantage of perimeters was the solution. The test samples have a 3x3 cross section, and the actuator pulls the pieces apart. The scale will read how much force it took to split the pieces. The 3D printed parts themselves had to withstand the force it took to split stronger pieces. I designed the parts with perimeters in mind to keep them as strong as possible. PETG could hold 42 pounds of weight, and nylon 11 could hold 106 pounds of weight on a 3x3 cross section.
For teams that are interested in making your own tension tester, at some point we will make the files available for you to print with links to the parts. Just reach out to us.
So over the summer, our team created a library for 3D designing and creating assemblies. This library makes creating assemblies easier and less time is consuming. The library has a collection of many Go Builder parts that we often use. Normally, you would have to use import file, and by doing that, you create a new folder, you create a new folder of imported files.
Is this the,
Um,
are you able to share?
yes.
Okay, go ahead and if I need to get out, I'll get out. Go ahead and share your screen. Oops.
Okay, I'm gonna share right
Go
now.
ahead. Yeah,
Oh, this is a drive train.
I don't think we don't see it. How do you share yours? He's sharing it. He is?
So this is a drivetrain model. By importing it, we created you would have to create two parts assemblies, and then there would be this CAD import section, and then there would import these files. But if you use derive from the FLL library, you only have to do this, and then you wouldn't have the imported files section. And with the imported files section, it can cause trouble because if you delete these, but then you might not know which one of these to delete. And if you delete the wrong one, then it'll cause missing files in the document that you used it in. And our FLL library has many different parts that we can use. This is Go Build a Structure. We have designed these different parts in a different document, and you simply click on one. You simply can click on one, and then you can choose the configuration number, and then it'll show you the part like this. Okay.
Okay, so the main purpose of the library for us was to make it lightweight because some of the members don't have very powerful machines. So our instead of importing multiple step files for the structure, we have a single part studio that's parametric.
The next thing I'm going to
Right.
talk about is fastening. One thing we noticed in teams, including ours, is that we have to use an excessive number of screws at each robot. Either too many screws or screws that are too long for their application. Countersink screws are not recommended for FFF because the angle head acts like a wedge, which will split printed layers apart. It's better to use a flat or sprocket head screws that spread the load evenly. Square nuts are a low-cost option for embedding in 3D prints. It's removable and reusable, and it's easier to use because it's a square. Heat set inserts are installed with a soldering iron to melt into the plastic, giving strong reusable threads. It's perfect for robot parts that need to be assembled or disassembled repeatedly. Dovetails are also an important way. They help align and secure 3D printed parts. With only a screw, the two parts, the part that's attaching to it could rotate and it could unscrew itself. But with the dovetail, it only allows linear movement, and with the screw prevents the linear movement, so the movement is restricted in all directions. It also reduces the number of screws needed to one, and the movement is locked to one plane. It keeps assemblies lighter and stronger, which is critical for FTC robots. Next slide. Like Alex was talking about in the SLS video, we designed models to test the tolerance because FFF is way less accurate. We have to 3D print these things to test the tolerances to find out which tolerance or which increased amount works best for different parts. Once dialed in, the holes fit the screws, shafts, and bearings reliably without extra drilling. Our Onshape library includes 3D printable parts with tolerances set for FFF, SLA, and SLS workflows. It also includes these test models. This table here shows the tolerance, the clearance, and the threaded for M4 screws. FFF needs a bigger clearance, and SLA and SLS don't need a clearance at all.
I think that's the last slide.
Yep.
Right? So after this, we can take some questions. What I wanted to offer FTC teams, or I don't know, maybe even FRC teams, is we will most likely open up our manufacturing capability to teams through our printers. As of now, Formlabs does not sponsor the material, so we don't know how that's going to work out yet. But I think GeorgiaFIRST will have a great advantage having access to these methods. So if your team is interested in exploring these 3D printing options, make sure to reach out, have your mentor reach out to us, and we can go from there. Let's see, let's take some questions. Are there any questions? Oops, is it in the team chat? It's this one. Okay. Most flexible, I would say SLA silicone.
That's the most flexible. It's not accessible.
Yeah.
Probably for TPU.
Yeah, I mean, for filament, it would be TPU, but the TPU is kind of like, it's soft, but it's also quite slick. So we're actually experimenting with TPU rollers for this season's game, but we do have silicone resin in stock for our final test if we need to go that route. Silicone is just much softer, and it is closer to rubber.
If you guys are familiar with the Go Build a Gecko wheels,
Yeah,
it's the same material they use.
but it gives you a lot of flexibility to be able to make your own parts. For example, I don't know if this is clear enough, but this is actually shaped like the ball.
There's a few questions in the Q&A section.
Oh, where's the Q&A?
It's like the same place as the.
Can you look for it?
Somebody asked where they could get access to the FLO library. I don't think we have.
They should email us, and we can.
It's not for FLO though.
Yeah, it's for FTC, but we are doing a slow rollout. We need help on maybe filling up the rev part. We've started just on the Go Builda. So if any team wants to help us build the library and work on the rev parts, then we can certainly share a lot of those. We will have links out for the test models. That one we will share almost immediately after this symposium.
And someone else asked, what type of printer do you use the most, and what is the best filament for that printer?
Oh, in my own farm, I have the most bamboo A1s.
So for
But-
our team, we most of the time for fast prototyping we use FFF. So just
Yeah.
regular fused printing. We use the Bamboo Lab A1 because it's fast and reliable to get all the prints done.
So
Yeah.
we typically use PETG filament with our Bamboo A1 too.
Yeah, so I mean, unless you're doing ASA and need an enclosed printer, I would say the A1 would be your best bang for the buck. But if you're now trying to say, okay, I want to make something like this, which is compliant, but it has a hard center. This one I actually printed in the Prusa XL because it's a multi-head. You can also do that with the H2D, but now you're going into $2,000 printer to $4,000 printer categories. Is there another question? Larry?
So, will these slides be linked anywhere?
I think GeorgiaFIRST is publishing the slides after the symposium. But for any technical questions, like even if you have models and you just want some help, hey, what's the best way to print this? Or what's the way to make this stronger? Yeah, feel free to reach out to the team, even either through Facebook or you can email us at team@firestormrobotics.org.
We have another question. What filament is the most rigid? I know ABS is very strong, but I think it's known for producing fumes.
Well, I mean, ASA pretty much has replaced ABS. It's a little easier to print. It doesn't smell as bad, but you still need a vented printer. For strength, it's hard to compete against carbon fiber nylon. Like the same model, like the one in Greg's tension tester, like PETG would break at 45 pounds, and we exceeded 100 pounds with carbon fiber nylon. And those little dumbbells, they only, like the dog bone samples that we made, those are only 3 millimeters by 3 millimeters in cross section, and they can support 100 pounds. It's quite amazing.
I think that's all the questions we have for now.
Okay. We're a little early, 5 minutes.
And wait, we have another question. Any types of clear filament for 3D printing? Transparent filament.
Yes, it depends on what you want. Like if you look at inland or bamboo, they're not very clear. They're really like more translucent. If you want something that's really clear, Green Gate 3D produces a nice clear filament, but you also have to print it slower. It's like don't use the default setting for PETG thinking that it will give you a clear output. Sometimes you have to slow it down at least 25%, so it gives you more time to melt the layers and fuse them together, then it will give you a really clear
It also has to
print.
be dry.
Yeah, it has. I mean, PETG need to be dry. So if you don't have one of those enclosures that's capable of drying PETG, then it's time to invest in one. Tough filament. Still, my vote would be carbon fiber nylon. What about you guys?
Yeah, it was very useful for us. Like the elevator, it was very stable.
Yeah. Yeah.
It warps pretty easily though, so you might need to invest in one of those.
Oh yeah, you need
Blue
one of
plates.
those blue bamboo plates.
Yeah, but it's
Called
also
cryo grip.
It's also really expensive. So
Oh.
maybe
Well, here's a tip. If you reach out to Polymaker as a robotics team and you have a 501c3, they might give you a couple of $100 of free filament. So I would use that to buy their carbon fiber nylon because it's very, very good.
But don't you need a diamond nozzle for carbon fiber nylon?
No, you
No,
just need
for-
steel. You
Or-
just,
or
yeah,
it's too-
any,
steel.
any
Too hard to
filament
steel.
that has fillers in it, like wood, carbon fiber, marble, you need steel nozzles. So if your printer has a brass nozzle, time to switch them out.
It's Polymaker that provides the hundreds of dollars of filament.
Yeah.
Any more questions?
I think that's, I mean, we can still, we have 4 minutes for questions, so if anybody has some. Um, if somebody wants to answer the queries.
It's called the CryoGrip Pro Glacier. It's you can buy it on
You buy it on
Amazon.
Amazon.
Yeah, it's on Amazon. If you want, it's just called. I think it's made by
CryoGrip,
Yeah,
yeah.
ByQ. It's a
Yeah.
CryoGrip
Or BQ.
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 Yeah, there's two
So-
types, and
Yeah,
we
that's
have the
definitely-
cyan one.
Do we just type it in?
Yeah, you can type it there. The IQU CryoGrip. Yeah. Too bad we don't have a lot of teams near us. I think the closest team near us is in Marietta.
Yeah.
Yeah. But if anybody wants a tour of the space or do shop talk on 3D printing, we'll be happy to oblige. Let's see. Yeah. That's not the one though.
They replaced them.
I like the PA12s. But I'll just send this one.
For what parts we used it for, we mainly just used it for the elevator. I don't think we had a lot of other heavy impact load bearing parts we used for last year.
It's really good for any parts that you need to be like small but also really strong.
Yeah.
So it's really good for many case scenarios, but that one in particular is where it shines.
Look at the Q&A. And then post. Resin printing allows us to print with a lot more engineering materials such as the silicone and many other materials. It's more precise than FDM printing.
Yeah, resin printing, the material choices you have for end use parts is just, it can't really compare with FDM. Especially once you get into like Formlabs, those are really engineering grade filaments. Like,
But they're also a lot better than FFF
Oh, yeah.
filaments.
Yeah.
Yeah. The only con is you have to spend more on engineering
Yeah.
grade.
yeah, the
Print.
resins are expensive.
Yeah. There's a lot of post processing you have to do.
You have to wash it and cure it.
Yeah, I remember our first time at the Formlabs booth, they showed us a sledgehammer printed with their durable clear resin, and we were hitting the concrete floor with it and couldn't break it. And it's like, wow, this one changed everything. Yeah. I
Any
think,
last questions?